All right, welcome to United Astronomy Clubs of New Jersey. We're back here on site in Jenny Jump State Park in Hope, New Jersey. Welcome for all of you who have joined us here. I see a few people coming and straggling down, so just to give them a couple minutes to, find a nice spot of ground or set up their chair. I do want to welcome you all and also welcome all of you who are joining us online because that is right, we do live stream this to Twitch and YouTube. So if you ever can't make it up and you're looking for something to do on a Saturday night at 8 p.m., do tune in, hit those like and subscribe buttons, ask questions. We love to see the questions in chat, and we go from there. You can also check us out on our website, uacnj.org. It's where you can find a list of all our upcoming talks, as well as a list of our previous talks with links to our those talks that we have saved and archived on YouTube. So if you look at our list and go, man, I really wish I had not missed that talk on the Fermi paradox, don't worry, you can actually see that particular talk. And if you have questions, feel free to go and ask those there in the comments. In addition, you can also check us out on our social media pages, our Facebook, Instagram, as well as our Discord channel. All great places to share your enthusiasm of astronomy. I know a number of you have shared your aurora pictures from 2 nights ago. They were awesome, I must say. So do go check those out. And if you have any questions, they're also a great place to get those answered as well. So we have a bit of a safety briefing for those of you who are here. First off, if you need to use the restroom, that is the porta potty in the back. To my left, your right, it is illuminated by red, so you can find it easily in the dark. We also have a little museum and gift area. I'll be manning that after the presentation because as of yet, they still won't give me the ability to be in 2 places at once. I think they're afraid that I would have way too much power if I could. So, unfortunately, like I said, that will have to wait till after the talk. In each of those sheds there, that has a roll-off roof, we have telescopes, and volunteers. If the shed has its roof rolled off, it is open and it has a volunteer running that telescope. Feel free to ask them questions, ask them what they're looking at, and do please follow their instructions if and when they give you any. When we go to leave here, it's also very important we are using our headlights because as much as we find them blinding, we much prefer the blinding headlight over the major medical bills from getting run over. So let's help us avoid that. No getting run over tonight. And despite that, because we use our headlights, we have a pretty good track record of not getting run over, and I'd like to keep that going. That being said, if we are wandering around and need flashlights to get around, because I know that feeling after monitoring online chat, I am night blind, so often you will find me. Do keep those flashlights or cell phone screens pointed towards the ground if we can, so we don't unintentionally blind people. With that, you're not here to hear me blabber on. You're here for a presentation about astrophotography with Mike Dzwinczyk. Mike is a chemist who worked with lab instrumentation in the pharmaceutical industry. Photography has been a lifelong interest, and with the growth of digital photography, he was able to combine his interest in astronomy with that interest in photography. He's been doing astrophotography for the last several years and must thank the UACNJ astrophotographers for their willingness to help, along with the internet resources that allowed him to take up and enjoy this challenging hobby. And with that, here's Mike.
Is that better? Okay. Well, I appreciate everyone coming out tonight. Astrophotography is a very big topic, so I'm just going to pick a few points and hopefully it'll be useful. The first thing is to get this going. Okay. Uh, Hopefully everyone can hear me. What I'm hoping to do today is to define, give you some calculations that can be used, the gear you need to do astrophotography, some of the newer things that are out there, procedures, in other words, what I do when I take an astrophoto, some objects to photograph, and some example photos. What you see on the screen is the North American Nebula with a little bit of the Pelican Nebula, and that was one of my early shots. You'll see a lot of stars. You'll see some larger looking stars, which isn't always good. And we'll talk about some ways of improving deep space astrophotography. So first, what is deep space? Deep space is any object you want to photograph that's beyond our solar system. And of course, the solar system is our sun, the planets, the moon. So this will not be about that. The objects in deep space are millions of miles away. And because they're so far away, often hundreds and millions and thousands of light years away. Because of that, it took the light a long time to reach us. So we're actually photographing objects in deep space as they existed hundreds, thousands, millions of years ago. And that's the speed of light. Even though it's 186,000 miles a second, it still takes millions of years for the light to reach us. That gives you an idea how far deep space is. And I'm talking about galaxies, and in our own Milky Way galaxy, I'm also talking about nebulas. And nebulas, you'll hear me refer to a couple times. They're gas clouds, and they're often familiar to people because they look like clouds, and people pick out objects in them, so they get named like the North American Nebula, the Pelican Nebula, according to what they look like. So photography is about collecting electromagnetic energy, and that's everything from your microwave to IR to UV to gamma rays. What we're talking about is the visible light, and the visible light is from something around 700 nanometers to about 430 nanometers, 400 nanometers. And what's important to understand is light, you'll hear me refer to a photon of light. It's a particle, and it vibrates at different frequencies. That's what you're looking at. And the reason that can be important, in other words, the colors of the rainbow is what we see with our eyes, and that's the visible spectrum. The reason that's important in astronomy is stars are not white. Stars, depending on their age, can be bluish, they can be reddish. Our sun, for example, is a medium-age star, and it burns at about 5,500 degrees centigrade, and it will look orange, reddish orange. There's other stars, and the younger stars that just formed in the nebula, the gas clouds, that's where the stars form, the gases condense. Those stars tend to have a bluish tint, and the reason is because they're burning very hot. And the reason they're so hot is when a star is first born, it's made of almost all hydrogen, so it has a lot of hydrogen to burn. And the more hydrogen it has, the brighter it is, the more blue it is. And so an example might be Rigel, which burns at 12,000 degrees centigrade, and it's a bluish color. Betelgeuse, which is on the Orion Nebula, is a red star, and the red stars are sometimes they're called red giants. They burn at a much lower temperature, something around 3,000 degrees centigrade. And the reason that's important is when you take an astrophoto through a telescope, you can see some of the different colors of the stars. And that's how you know you're getting a good photo, when you could pick out some of the colors you haven't saturated the color. So what do you consider for to get good astrophotos? And everything comes down to the photons of light you can collect. The more photons of light you can collect, the better your pictures will tend to be. And so the things that affect the amount of photons of light you collect is, of course, the opening size, the aperture, and the focal length of your telescope. The bigger the telescope, the more photons you can collect. The camera sensor, the efficiency of the camera you're using. And the other type is there's different types of cameras, and some are even cooled. And the other thing in astrophotography that's very important is to try and reduce the noise, the background noise. Because it's not like taking out your iPhone and taking a photo. That's instantaneous. With astrophotography, you're opening up the shutter of the camera for minutes at a time. Sometimes 5 minutes, could be even longer than 5 minutes. So you get a lot of noise. And some of the reductions in noise you can consider. To reduce them, you have to avoid any motion. Post-processing. Astrophotography really wouldn't exist if it wasn't for stacking of your frames. So when you take multiple frames, you stack them on a computer afterwards in post-processing, and the noise gets less and less. I'll talk about that a tiny bit. Elevation of your object. If it's almost straight up, that's good, because that means you're going through less atmosphere than if you're on the horizon, because on the horizon you're actually going through more atmosphere, and the more atmosphere you go through, the more noise you introduce. Other things like the temperature of the camera sensor matters, because if you're leaving the aperture open for 5 minutes, those photons of light are hitting the sensor and it's converting it to electric current, which means it's heating up. So astro cameras, unlike your regular cameras, are actually cooled. The sensor's cooled to keep the noise level down. Another very important thing to consider is where you take your photos. And there's something called a Bortle scale, which is a darkness scale that astronomers use. And it goes from, I want to make sure I get this right, from 8, 9 down to 1. And the lower the number, the better, the less light pollution there is, the better the darkness is. This area here, well, I live in Parsippany, and there it's about a 7 Bortle scale, which is not good. A lot of light pollution. Here, it's about a 4, which is much better, but it's still not great. If you go to Acadia National Park in Maine, there's a section of it that's a Bortle class 2. And I've taken a photo there, and it's magnificent. And the difference, here's a couple of photos I took of the Orion Nebula, the Sword of Orion. And you could see on the right hand, on the left hand side, if the skies have a lot of pollution, you can't expose it as long, and so your images aren't as bright. The image on the left is a, a processed image. There's other factors here besides the darkness of the sky. It was different processing and different exposure time, but you could see why it's important to try and shoot in a dark area so you can get the fine details of something like the Orion Nebula. One improvement that you can try, and I use filters, light pollution filters, and in a quick summary, what they do is, and you could see on the left, the graph shows you exactly which wavelengths of light they allow through and which ones they block. Because a lot of times there's no need of collecting all the light, and so if you can collect just the light that you're interested in, what happens is your background gets darker, and that's not quite the same as having dark skies, but it helps. If you want to do extreme, there's something called narrow band filters, and narrow band is something I've used to take nebula. It applies because it cuts out almost all the light. The only two wavelengths of light, and when I say wavelength, you could think of colors of light it allows in, are here. It's 656 nanometers, which is, by the way, a red color. And it happens that hydrogen, ionized hydrogen, which is what these nebula are made of, is mostly hydrogen. So if you have an emission type nebula you want to take a picture of, this filter works wonders. It also lets in oxygen, and oxygen absorbs at 500 nanometers, which happens to be blue. So I'll show you a picture taken with a narrow band filter, and that is right here. Now this is taken probably from here. I'm sure it was taken here at United Astronomy Observatory. It's the Horsehead Nebula and the Flame Nebula. And you could see on the right side, you can see a little horse's head sticking up. I hope you can all see that. And next to it is the Flame Nebula. That kind of looks like it's on its side, but it looks like it's on fire. That's a popular topic. And even though this is a nice photo, you notice it has a tremendous amount of red. It brings out all the details in the red color, the hydrogen. It's called the hydrogen alpha wavelength. So let's get back to taking good photos in deep space. This photo here is on a tripod with a SLR camera that does not track the stars, because you look up in the sky and you see the stars are moving if you watch them over time. Actually, the stars are not moving. The Earth is rotating, so you're moving, so it makes it look like the stars are rotating. And by the way, when you get a photo like this, the dead center of this photo, that's Polaris, the North Star, because that's stable in one spot and all the other stars rotate around it. So we're very lucky to have it, because when you do astrophotography, you do a polar alignment on that point to make your tracking good. Now you could take pictures, of course, of constellations, star trails, the moon, comets, meteors, with just a tripod. And I'll show you a couple photos I took with just a tripod. When I began astrophotography, I wanted to get the moon, which is a nice target. It's easy to find. And I used my 600 millimeter Sigma lens and my Canon SLR camera on a tripod, and I got a nice photo. On the left side, you see that it's very hard to see, but I did get a picture of Jupiter with 4 moons. But it's not a great picture, of course, but it shows you the capabilities of just a tripod. Now, did not mention one thing that you can take with a tripod and a still camera, and this is the recent auroras. And this photo here, it's an amazing photo, I think. I thought you'd have to go to a place like Alaska to get a photo like this. This was taken by the United Astronomy Club member, Samir Patel, and he went just a little bit over the border into New York State on, I think it was Thursday, this past Thursday, and he got this photo, but he went put it on a computer and enhanced it. So when you see this aurora with your eye, it's just a red glow. The sky is glowing red. You don't get the details because this was a 6-second exposure at ISO 800. So, and it has a lot of work up in the computer. Here's a photo I took in Acadia Park in a dark site that was amazing. There was no moon, and you looked up and you just saw the Milky Way going from one horizon to the other horizon. That's a Bordeaux Class 2. And I was able to take this with a 15-second exposure, and I did some manipulation in Photoshop because the ground in the foreground would be black if I didn't. I took 2 photos, one of the foreground and one of the Milky Way for 15 seconds and combined them. So you can get some nice photos even without a lot of expensive equipment. So that's where I started, and those of you that have tried this and have taken pictures from a stable tripod, you may be saying, why don't I get star trails? And you will, if you leave the exposure long enough. But luckily, someone came up with a formula so you could determine how long an exposure you can use before you see star trails. And that's called the 500 rule. And it's down here, I underlined it. It's 500 divided by the focal length of your lens or telescope. And that gives you the maximum time in seconds that you're going to expose the shot and not get star trails. And so as an example, if you have a telephoto lens, a 300 millimeter, and you put it into the formula, you get 1.6 seconds. That's all you can expose it. So you're not going to get a great shot of the Milky Way with a telephoto lens. If you use a wider angle lens, like a 50 millimeter, which is wider, you put it into the formula and you get 10 seconds. Well, that's better. And so for taking pictures of the Milky Way, what you want to do is you want to use a very wide angle lens so you can expose it for 15-20 seconds and get all the details. Now, to do real astrophotography deep space, here's some of the equipment you need. You have to have a tracking equatorial mount so it'll follow the stars when they move when you're taking 5-minute exposures. You need a telescope, you need either a cooled camera or a SLR, you need a timer or a computer, you need a power source, either plug-in or there's a lot of things. You need, and for the more advanced of you that want to take pictures like I'm about to show you a couple, you also need a guide camera and a guide telescope because the mounts, even though they're tracking very accurately, they can't do a good enough job because any slight movement of the stars will cause fuzziness. So what you do is you have a second telescope that's focused on a few stars and a secondary camera, and what that telescope, it's called the guide scope, does is it As soon as it sees a star move a slight amount, it sends a signal to your mount to correct it, to keep it exactly on the stars so you can take your 5-minute exposure and work it up. And then you need focus. Focusing is so important. You can't just hit autofocus and expect to get good focus. You have to have very precise focus because you're talking about exposures of several minutes. And there's something called a Bahtinov mask that I used to use, or electronic autofocusers, which is the best way. You need control software to control all this, and when people start, they never think about the do. You're out there in the middle of a mountain someplace like here, and when it gets dark and colder and the temperature drops, and it's high, if you have high humidity, what happens is the dew forms, and it forms on your lenses, and your shots are no good. So you have to have heaters that will come on and keep your telescope a little bit warm so the condensation doesn't form. Now, I'm going to show you a photo I took in September last month. We went to a star party at Cherry Springs, Pennsylvania, which is one of the darkest sites on the East Coast. It's a Bortle 2. And I was lucky enough to expose this for 14 hours. Excuse me. And that's the Cocoon Nebula. And you could see a dark nebula trail behind it. And you notice all the stars. A second one I took at Cherry Springs, it shows two sets of galaxies clusters. On the lower left is something called Stephan's quintet. And on the upper right, the upper right is something called the Dirichlet group. Galaxies often form in groups also, so you have billions of stars in each galaxy, and there's groups of galaxies, and with the right equipment and the right location, you can get this type of photo in deep space. I have some, thank you. That was almost a short presentation. When I started, I got a very small Skyguider Pro mount on a tripod. Then as I improved, I got a more advanced telescope with a higher quality mount. And you could see the list of, there's flatteners and there's guide cameras and there's flats for collecting. You have to have a light for collecting flats and darks, dew heaters, batteries, special filters, table and chairs. So there's a lot of equipment you need. Of course, if you really get hooked on the hobby, you're going to want a bigger telescope. My wife appreciates when I set my equipment up in the living room, as you can imagine. But this is my big telescope. There's much bigger ones, but for me, it's an 8-inch reflector. It's an RC8, and it allows me to get some of the photos like the ones you saw of the galaxy clusters, because you really need the reach of a large telescope in order to pick out these small galaxies. With a couple exceptions, Andromeda Galaxy being one of them, you don't need as big a telescope. Now, when you want to improve your astrophotography, the things that we do is we go to electronic autofocusers, so you don't have to manually focus. It's more accurate. It uses and it's automatic once you get rough focus. Filter wheels, you don't have to have a drawer with putting in filters. Filter wheels could take up to 7, 8 filters at a time, and automatically, depending on the program, switch. There's now dual sensor cameras, so instead of having 2 telescopes and 2 cameras, one for guiding, one for photographing, you have both sensors on one camera, so you can do things simultaneously. It does the same thing as a second telescope. And finally, lately, the innovation has come to the mounts, and the harmonic drives are out. The harmonic drives are fantastic because they're a little bit more accurate and they don't weigh a lot. The old ones used to weigh a lot more because they had to be stable, and they also took counterweights, so you had to balance them in order to get good tracking. With the harmonic mounts, they don't have to be balanced, they only weigh a few pounds, and there's no counterweights, so it's something I really like using. Oh, let me go back for a second. The other thing is, hopefully we have time, but there's fully automated setups now. So everything I'm going to tell you is, I don't want to say ancient history, but to get good photos, you still have to do it. But there is more and more automation. Just look at your iPhone, what the camera can do from a few years ago. The same thing is happening slowly to astrophotography. Here's what you can expect if you get into astrophotography. You see on the left my first photo of Andromeda Galaxy. It was terrible, but I was proud of it because I could see it wasn't a star. As you get better, your photos get better, and the processing is a big thing of it. If you don't take something like Andromeda Galaxy with just a good tracking mount and a SLR camera, one of the members of our club here took this. And this is a very nice photo. It shows 2 galaxies, Bode's galaxy and the Cigar galaxy, in a field of stars. And you can expect to get that with an SLR camera. If you get a bigger telescope and you're able to get all the other equipment, you can get the same Bode's galaxy on the left, Cigar galaxy on the right, and I blew up the Cigar galaxy so you could see some of the fine details. And that is what most astrophotographers doing deep space are after, to get some details in their object. I'll show you Andromeda Galaxy, my current, this year's version, after the workup. And here it is. And I'm also proud of this one because I got a lot of detail, and you'll notice there's a lot of stars, and if you look carefully, you could see that some of the stars have color. I could see a reddish orange star in the upper portion. Well, that's an old star. It's not burning as brightly, remember? If you see a bluish star, and you could see that the Andromeda Galaxy itself, you can see a blue tint around the outside edge. Well, those are all new stars that were formed. And so you also have dark bands. And that's some of the details. And the core is not blown out. So this I would consider a good astrophoto. It has a lot of details, and you can use it to impress people with. So what are the elements to make a good photo? It has to be, the mounts have to be balanced unless it's a new harmonic mount. You have to get a very accurate polar alignment. You have to get a very good focus, whether you use electronic focus or the Bahtinov mask, one of them is going to be required. You have to have good guiding accuracy. And sometimes when you don't get a good polar alignment and your mount isn't working well, you just get oval looking stars. and that's not a good photo. You have to get round stars. That's how you could tell. Good seeing conditions are, of course, a important factor. And when you do deep space astrophotography, you have to not just collect the light, the stars. You have to collect dark frames, bias frames, flat frames. That's more work. And I'm not going to go into too much about this. If you get into it, you'll learn that what these things are. And there's a lot of different software, and the software is made to do different things. There's software for shooting the stars, like Stellarium, Astrophotography Tool, Nina, PhD2, and the ASI Air. Then there's software you have to use for processing, things like DSS, Deep Sky Stacker for stacking, Surreal, StarNet, Photoshop, or Pixel Insight. That's the big one that a lot of people use. I'm just throwing these out at you in case you get into it. You'll see that there's a lot of tools out there. Most of these are free software you can download from the internet. Some of it is you have to buy. And I think I mentioned this already, the filter wheel, the electronic autofocuser, the dual sensing cameras, and the harmonic mounts. That's kind of the latest technology that people use that do a lot of deep space. If you want more information, or if you get into the hobby, there's a couple of websites I want to point out that are invaluable. Astronomy Tools website, it'll help you decide whether the camera you're using is suitable for the telescope you're using, so you're not oversampling or undersampling. It'll tell you the pixel size, the resolution, guide scope suitability. It's got a lot of formulas, and you can simply put in your gear and it'll tell you where you stand. So I found it very useful when I started. The other one is telescopius.com, and that gives you targets. If you want to know what could I shoot tonight, what's out, that's a good site to go to, and you could put in your gear and it'll show you the framing you'll get, so you can plan your trips and your astrophotography nights with that. There's a lot of other things it'll do, like panoramas and recommended viewing angles, information about the targets, and so forth. Now, I'm not going to spend, let me check my time. Oh, good. Because I could spend an hour on this slide, because this is the procedure for astrophotography for deep space. And initially there's the setup, and I'm just going to read them to you so you get an idea of the extent that you have to get into this hobby seriously. It takes time. You have to point the tripod north, because you're setting up the tripod before you put the head on it. And you then have to mount the mount, an HEQ5 in my case, and the mount goes onto the tripod, and then the telescope goes onto the mount, and then the guide scope gets mounted on, and then if you need to, you put counterweights on, you make sure your dew heaters are on, and then you balance it to make sure that the motors can drive it, the mount. So that's to set up, and that usually takes half hour, 45 minutes to do. And then you have to wait till it's dark enough to see the North Star, because then once the sky is dark, and let's say you use an ASI Air, which is an automated system, you have to do an accurate polar alignment. That's critical. You have to find, center, and focus on a bright star, and then you do your focus. You make sure that star is as small as possible. That's what the focus, or the Badenoff mask will help, or electronic autofocus. Then you have to take a test. You have to find your object. So you have to either know where to go or let the computer guide it to your object you're shooting tonight. Maybe it's Andromeda Galaxy. So it'll go to Andromeda, and you need to center it, and then you need to start the guiding procedure. Then you need to run your procedure for collecting the light, and then you collect, in the case of Andromeda, maybe 4 minutes, and you collect for maybe 2 hours, 2.5 hours, maybe 14 hours over 2 nights. It depends on what you're shooting. After you collect all these light frames, you have to, you collect the light frames, you have to collect the flats, darks, and dark flats. That's to help your processing to get a good background that's flat. And then you have to work up the photo at home the next day, the next week, the next month, using all this information. I'm now going to show you what Andromeda looks like with one 4-minute exposure. That's it. Now, it may not look like much, but actually it's a lot. There's a lot of information there. And those of you that have a chance, you can maybe see Andromeda through one of the telescopes that's set up, and you won't even see that much detail in, because remember, your eye is not open for 4 minutes. It's open for a split second. And so you don't get as many photons of light going into your eye, so you shouldn't expect to see this kind of detail when you look through a telescope, even a big one. Of course, when it comes to, if you do the 2 hours, 2.5 hours of those subs and you work it up, you could work them up different ways. You have a choice how much color to put in, and I'm going to show you one picture I used to like, and this I now consider grossly over processed. In other words, the colors are too saturated, the stars aren't as small as they should be, they're bloated. But in the early days, I loved this photo. I thought it was great because I got the colors. I got a little blue in the Andromeda, I got the dust lanes. And just so you have a frame of reference, this same photo taken this year, there it is. And now maybe next year I'll think this isn't that great, but it's a good photo. The stars are much smaller, tighter. My tracking was very good. It's clear. You can see 2 other satellite galaxies, by the way. The fuzzy ball on top and the oval ball on the bottom are satellite galaxies of Andromeda. So you're looking at 3 galaxies, and Andromeda is one of the largest galaxies. It's the closest one to us. It's about 2.5 million light years away. It's the closest galaxy to us, and it's much bigger than the galaxy we're in, the Milky Way. It's about, they estimate that the Andromeda has about a trillion stars. We have something like just under perhaps half a billion stars. I'm sorry, 500 billion stars, something around there. So Andromeda is much bigger. And this was a 3-hour exposure from this site with my telescope. And stacking, I mentioned it a couple of times, astrophotography wouldn't exist if you couldn't stack. The programs line up your images automatically. And the important thing about stacking is the noise reduction, because when each individual frame has a lot of signal noise. So the signal to noise is low. When you stack it, your signal to noise improves dramatically, and you could see it when you process it. And I put this up because how do you know how much noise you're going to reduce? And if you have the frames and you do good processing afterwards, by doing stacking, there's actually a formula. It's actually the square root of the number of exposures you get. So the more exposures you get, the better your noise is going to be. And so what that means is that if I take 4 5-minute exposures and I stack them, the square root of 4 is 2, which means I'm going to lower my noise by a factor of 2. It's going to be twice less noisy than if I didn't stack at all. And you can imagine if you do 25 light frames, so you take 25 5-minute exposures in the dark, in the cold, and when you're processing, you stack them, your noise level goes down by a factor of 5. And that's significant. That's why I said you wouldn't get such nice photos if it wasn't for stacking. That's the big thing. And those of you that are interested, I guess the talk will be on the website. You could read about dark frames, bias frames, and flat frames. I kind of describe them here so you can have an idea of what's involved. I'm not sure why I put this in here, but I always wanted to take a photo of the Pleiades star cluster, because you can look up and you could see it, especially in the winter. It's not, and it's a group of stars, the Pleiades, sometimes called the Seven Sisters. What I like about it is I have a Subaru, and the emblem of a Subaru is the Pleiades star cluster. People don't realize that, but that's what it is. And when you take a longer exposure, even of stars you could see, in this case, there's nebulosity around the stars, and that's the blue. And you could also see the different colors. There's on the left side, you'll see a nice red star. The one that's really popular is Orion, because people could find it, and Orion has the belt. And if you look at the sword hanging down from the belt of Orion, you take a photo of it with a short exposure, that's what you see. You see that the middle star isn't really a star, it's a nebula, it's a gas cloud. And if you get a longer exposure and a better telescope, you see what happens is it really comes out. When you process it, you could see that the Orion Nebula is significant. And the Orion Nebula, even from a not the darkest sight, is spectacular, because when you process it properly and you take along many exposures, you can get something like that, where you have the nebulosity, you get the color, and right above the Orion Nebula, you see what's called the Running Man Nebula. And so you get 2 for the price of 1. Now, I mentioned improving astrophotography, and narrowband filters is something that this was broadband. But if I took the same thing with narrowband, it would look like this. And I did that. It's on its side now. But you see what a difference you get? And the difference is important to scientists, because a lot of times when they're studying the stars and nebula, they want to understand what's hydrogen, what's oxygen. Remember the narrowband filter I told you about? It lets in hydrogen and oxygen. The hydrogen is red, orange and red here. The oxygen is blue. So you can see the blue nebulosity is all oxygen. So you get a lot of information from narrowband filters. And for some nebula, it's really required. The other thing that you do when you do more advanced astrophotography is you remove the stars when you process the nebula, so you could enhance it properly, and then you put the stars back and you control the size of the stars. And this is a photo that shows that process. The bottom, you could see, has a lot of bigger stars. The top photo is a better photo because the stars are smaller and there's less of them, and you see the nebula stands out better. And that's done through some software that you can get. StarNet is the name of it. And you could do that with almost any photo. This is the Whirlpool galaxy about 20 million miles away. And I did that, and I was able to get a nice colors. Uh, and the Whirlpool is an easy target to photograph because it's somewhat bright. So for improving the signals and noises, everything, you can see here a couple of broadband, a North American nebula, a couple of broadband, which is collecting all the wavelengths, and it tends to saturate. I'll show you a photo I took this year using my narrowband filters, and I processed it properly. Well, this is another one with narrowband, but I didn't know how to process it as well. When you process it properly, that's what you can get. And this is one of my favorite photos that I've taken because it shows really nice color where the oxygen is. It shows the red of the active star forming regions, the hydrogen regions, and it shows and you can see on the left side, the nebula, the gas cloud looks like the North American continent. And on the right side is something that was named the Pelican Nebula because it looks like a pelican. You can see its beak looking towards the North American Nebula. And again, if I go back to the narrowband image, has a tremendous amount of information, but this is not a good nebula for narrowband. The reason is because it's got too much hydrogen and not enough other things. So it's better to shoot it in broadband not using a filter. And this is a photo where you get star color, you see how the flame nebula is a different color from the background of the Horsehead Nebula. And next to the Horsehead, there's a nice blue nebula that's also part of the photo, and it makes for a nice photo by shooting broadband. So keep that in mind. Not everything is better in broadband. And some things you can take from a light with Bordeaux 7. I took this photo from my house in Parsippany, and this is a nice photo. It's a shorter exposure. I think I only exposed it for 60 seconds at a time, but I took a lot of exposures, and even though you're looking through a telescope, you wouldn't see it. By taking a lot of exposures for an hour and a half or 2 hours, I got a nice M13 star cluster. And I took this, of course, with my big telescope because a lot of the star clusters are small. And a star cluster like this has thousands of stars in it. You can't see them all, but because the core is so bright. So there's a lot of interesting photos. One of my favorites, and it's easy to take with narrowband, it's almost made for narrowband, is the Helix Nebula. I was here Thursday shooting it. This is not actually that photo. I haven't processed it yet. But what's nice about it is, first, it looks like an eye, doesn't it? With an eyebrow there. And the blue is the core of it, and it's the oxygen, and the red around it is the hydrogen. And this is a remnant of a supernova explosion once, and that's what you get. I'll just show you quickly the Pac-Man Nebula. Again, a good one for using a narrowband because you get the blue and the red color. And it's something that's referred as HO photography, hydrogen and oxygen HO photography. I'm going to speed it up a little bit more because I have a lot to show you. Another supernova that exploded 10,000 or 20,000 years ago was very bright on Earth. A supernova is a collapse of a red giant star, and it stays very bright for a week or two, and then it fades. What does it fade into? it fades into a nebula. And this is what the nebula looks like from that 20,000-year-old explosion. It's called the Veil Nebula. And you can kind of see that it's rounded. It's a round shape. And I could remove some colors I could remove some stars to improve it. And of course, I could improve the colors even better. And if you have a big telescope and you look at the lower portion of it, you see a lot of filaments of gas. And what I did was I took my big telescope, because this is a very large nebula. So you use a wide angle. This was shot at 280 millimeter telescope, and this was shot a small portion of it, what I'm about to show you, with my 1600 millimeter telescope. So if you look at a small portion of it, you can see the oxygen and hydrogen, they're filaments left over from the explosion. So I like this photo because it does show the difference. I'm not going to go into electronically assisted astronomy, but there's a way of taking photos, short exposures, and stacking them in real time. And what you end up getting is photos like this, which are much better than you could see with the naked eye looking through a telescope, and photos like this, which is fantastic for a night like tonight. If somebody had electronically assisted astronomy, you could see this, and you could see the Veil Nebula on the left and the whirlpool on the right. So the question becomes, is there an easier way to improve basic astrophotography? And the answer is maybe, or it's getting there. There is a C-Star S50 automated astrophotography. Whether it's an improvement or not is out, but what you see on the slide is the entire setup. It goes on a tripod. You tell it to go at night. It does everything else. It focuses. It does the polar alignment for you. It finds the object you want to photograph. It centers it. It takes the picture, and the whole thing will weigh 6.6 pounds. There's more sophisticated ones coming out, so the technology is improving now. But what's nice about this is it's got a built-in telescope, camera, tracking mount, focuser, all in one equipment, and it could look at the stars. It has a setting for the moon, for the sun. It has an actual filter that goes on, and you can even take scenery with it. So what kind of photos does it take? Well, it's the very beginning, but for an inexpensive setup, it's quite impressive. And I've had astrophotographers tell me they like it because they can show their kids in one night and email people pictures like these. On the left is Andromeda Galaxy taken with the C-Star over just a few minutes. Oh, well, it actually used, it was 55 minutes in the city, though, not a dark site. And on the right is, remember I showed you the Cocoon Nebula? That's the Cocoon Nebula. So it still has a long way to go to just a single 4-minute exposure with the equipment, but it is something that you'll see more and more improvements on. And it's certainly for beginners that want to dip their toe into the hobby, just a few minutes to glimpse targets. You'll never be able to see through a telescope in a city. So it does improve on that. And it's a gateway drug to astrophotography. If you get this, you won't be satisfied after a few nights. You'll want to get better resolution, better shots. So that's what you'll get. So there's a lot of advantages to it. And how's my time? I think we're almost done. So I'm gonna skip over the tracking. You know, it's a natural progression when you go get into astrophotography, from no tracking to simple tracking to a complex setup that does everything, and it's getting easier because there's the ASI Air, which automates a lot of the software. So the quality is going to go up. The biggest concern in astrophotography these days is dark sites. There's, there's starting to be more pollution. Even here, it used to be better. The Milky Way was more visible years ago. That's what I'm being told. Um, so the summary is collect all the photons you can. That's the important thing. And any way you can to do that, larger telescope, darker sights, longer exposures, better cameras, more efficient, that's the way to do it. And that's a photo I took in honor of Halloween. I took it last year from this side. It took 2 or 3 nights of exposures, but I don't know if you can figure it out. It's the Witch Nebula. It's near Orion, and it's a big nebula, and it's the Witch is looking to the right, and you can see its nose. And one more for Halloween. This is the Ghost Nebula, and to get a good shot, you do need a dark side, and it takes a big telescope. But you can see people name them according to what they look like. And the reason I love deep space, it's a challenging hobby. You have to really like a challenge to get good at it. A lot of people spend a lot of money, a lot of time, and they struggle. But if you join a United Astronomy Club or a place like that, there's other astrophotographers that are here that will be glad to help out. And some of them have been doing this hobby for 15, 20 years. So they've really seen it all. So thank you.
All right. Thank you so much, Mike, for a great talk. So we are going to be doing a question and answer session. Haha. This is why they give me the remote. Like, I don't know why they those lights keep turning white. We are going to be doing a question and answer session. However, I did see a number of you sneak in after I had already given the safety briefing, and the safety briefing is inescapable. No running away now. You have, if you need to use the restroom, you have the porta potty in the back to my left, your right. It's illuminated by red. We also have a museum area and gift shop, which I will be manning after the question and answer session. We do have a number of telescopes open, run by our volunteers. Do ask them questions. Do be mindful of them. They usually love to answer questions unless you kick their tripods, and then all bets are off. When we go to leave, we are using our headlights because, again, we like to not get run over, and I am sure you feel the same way. If we are wandering around with like a flashlight or anything like that, do try and keep that light pointed towards the ground. We don't need to accidentally blind anyone unnecessarily. Even though we use our headlights, that's more of a safety thing because motor vehicle versus squishy human being, motor vehicle usually wins. So, how question and answer is going to work? The people here, you're going to raise your hand and wave it about, and I'm going to bring you the microphone to ask your question. For people online, you have it easy. You get to just type. And I'm going to start it off with our first online question, which is, can you make a picture out of microwave data? What would that even look like?
The answer is I don't believe you can, because it's a whole different frequency. The wavelength ranges are very different, and what happens is your eyes are looking for colors. Remember the 400 to 700 nanometer wavelength region? That's what we see. So it's not possible to get an actual microwave picture, as far as I know.
I would imagine if they collected the data, they could probably do similar to what they did for image of the image of the black hole, where they collected all the X-ray data and then algorithm and mathed it into a visible picture. And I don't know how to do that. Um, but I imagine there's someone smart enough who could probably figure it out with enough time and money.
I I'm not sure.
So, all right, question now here. Cool, I see one in the back. You put your hand down. I lost you.
I was curious to learn how you use the pictures, like scientifically. Do you share them with researchers? Do you put them in art shows? Like, what are the things that you end up doing with the different photographs you take?
Okay, that's a good question. I I don't share them with other people except uh, through emails here at United Astronomy. Friends, family, they're all impressed, of course. The scientists have much better equipment, telescope, ways of correcting for turbulence in the atmosphere, which I don't do. The photos I take are for my use, and I have actually, right now, there is a small show at Morristown Memorial Hospital that I'm in, and I featured some of my astrophotography uh, uh, photos. So if you want to see some of my photos printed, they are at the Morristown Museum, Morristown Hospital, the main hospital in Morristown. But for the most part, I enjoy sharing them with people, and it's always important when you share a photo to share details about how big this object is, where it's located, how long you had to expose it, uh, and how many light years away it is, because people are amazed by it. I myself am amazed that we can take photos of galaxies millions of light years away, and therefore millions of years ago when we look at the light. So these photos are nice, but they're not scientific photos.
He is also being very humble. He's one of the featured astrophotographers in our calendar that we get printed yearly.
I forgot
So,
about that.
yes. So you too can own one of his images. Ooh, ah. I if I had one in my hand, I'd be like Vanna White here, but imagine I'm holding it up. Okay, so our next online question. Is there a point where no matter the amount of photons you collect, you're, uh, hold on. Is there a point where the amount of photons you are collecting has such a diminishing return that it is no longer worthwhile?
That's a really good question. The amount of photons is more a photography question. Diminishing returns is real. You can get a nice photo in 2 hours, uh, and you'll get a better photo in 10 hours. How much better a photo will you get in 20 hours? That's the diminishing returns. But the other end of the photon collection is more important, and that is you have to be careful not to saturate your photo. Those of you doing photography know if you overexpose something, you saturate it. Well, if you use too big an aperture and you expose too long, you'll saturate your stars. And there's a way to avoid it, because when you use the software and different softwares out there, it'll show you a histogram of your light distribution in a photo. After you let's say you take a 5-minute photo, and you look at the histogram and make sure you're not off on the right side where it's would be saturated. But collecting photons, the more you get, the better, and there is no limit. Uh, there are photos, I've seen collaborations that were over 60 hours, 100 hours. And yeah, they're nice, but the processing probably made a bigger difference than the photons. Thank you for the question.
All right. Was there another question out here? Bueller? Even the cricket stopped that time. That was kind of weird. All right. So our next online question is, what is the one quality of life piece of equipment or gear that you got for doing astronomy that you never ever want to go without again?
Well, that's a really tough question because um, you cannot do astrophotography without a tracking mount, at least the type of astrophotography I want. So I would say a tracking mount is the most important piece of equipment you have. It's more important than a telescope, more important than all the electronic gizmos you do. Uh, and if you're going to spend money, spend it on the tracking mount versus the telescope. Get a cheaper telescope and a more expensive tracking mount, you'll get better results. So that's the only way I could answer that.
Now, I'm not into astrophotography at all. The one quality of life piece of equipment, a comfortable chair that reclines.
That's important too.
That, and when you're here, bug spray. Definitely bug spray. But that's besides the point. I just thought that was a good question. Anything out here? All right. So online people do get those questions in. Because if no one has questions here, I want to make sure you guys have time to get those questions in. Because by the time they hear it online, we've already moved 3 minutes into the future. We are time traveling and an absolute sprint. All right. So our next online question is, what is the Discord server? And I know you're not going to know this off the top of your head. Our Discord server is actually, well, in case your question was, what is Discord? Like, not even aware. It isn't, and I had posted this online. It is a free app that allows users to communicate with each other through text, voice, and video chat. A lot of gamers use it as a way to be like, hey, here's the room for chatting about Stardew Valley, Minecraft. You know, we have other communities such as cooking, or us astronomy have moved in to try and form a community of like-minded individuals where we can share things like our images, ask questions, be like, hey, I'm having problem with my telescope setup. Any tips or pointers on how to fix that? So that is what that is, and I did link that in the chat through our link tree. If you guys have any questions, like I said, just raise your hand and I will bring the mic to you. All right, so our next online question. Are there still nebulas left to discover or name?
That's a good question. There's several catalog numbers for almost every nebula. If you were to find one, it is possible that you could find one. Of course, it would probably be very obscure, very small, very dim, so you would need some sophisticated equipment. A normal telescope with a normal setup for astrophotography, I think it'd be very difficult to find a new one.
Yeah, at least probably until we start heading out into space a little bit more.
Perhaps.
And then things get closer.
And remember, we're in the northern hemisphere, so we only see half of them. The other half are in the southern hemisphere, or at least a little bit less than half.
All right. Anything? All right. So just to give us a couple minutes in case anyone thinks of anything last minute. Once again, thank you all for joining us. Thank you, Mike, for the presentation. If you happen to see us online, on our YouTube or Twitch, do hit those like and subscribe buttons. They're completely free actions that let us know we're doing a good job and helps us get out our love of science and astronomy to as many people as we possibly can. In addition, check out our like I said, check out our website, uacnj.org. We have links upon links upon links to various resources, pages telling you about what telescopes we have, what science is going on at the observatory, as well as links to our member clubs, because we are a club actually made up of other clubs. And the best thing you could do if you are interested in astronomy at all is to actually find your local club and go talk and visit with them. Because if I'm out here in rural Warren County, New Jersey, what I know to be tips and tricks aren't necessarily going to be so helpful for someone who lives in Parsippany or New York City. And we do have member clubs who are based out of such places. We have clubs in New York City who have volunteers who go out and do sidewalk astronomy. So do check out our member clubs. We love to see their membership grow and the love of astronomy flourish. And it looks like that is it for our questions. So like I said, everyone have a great night. The skies are finally clear. But that's all.